In this section, we apply double integrals to the problem of computing the area of a surface. Suppose that we have a surface S that is described by the equation z equals to f of x comma y, where x and y belong in the region D that lies below the surface S, and the function z equals to f of x comma y has partial derivatives fx and fy that are continuous. Then in this case, the area of the surface S will be given by the double integral over the region D of the square root of 1 plus fx to the square plus fy to the square times dA. And if we use the alternative notation for partial derivatives, then the area of the surface S will be given by the double integral over the region D of the square root of 1 plus partial z partial x to the square plus partial z partial y to the square times dA. Let us see an example on how we can find the area of a surface. Suppose that we have this equation of the plane 3x plus 2y plus z equals to 6, and we want to find the area of the part of that plane that lies in the first octant. So starting from what we are given, the equation of the plane 3x plus 2y plus z equals to 6. If we solve for z, we'll get that z equals to 6 minus 3x minus 2y. So that means that z equals to the f of x comma y, which is equal to 6 minus 3x minus 2y. The plane z equals to f of x comma y intersects the xy plane when z equals to 0, which means that 3x plus 2y equals to 6. So the plane z equals to f of x comma y intersects the xy plane in the line 3x plus 2y equals to 6. And if we solve for y, that will give us that y equals to 3 minus 3 halves x. So if we sketch the region D, it would be a triangular region. So this is y equals to 3 minus 3 halves x. And here we have the point 2, 0. And here the point 0, 3. We have y, x. So this is the region D over which we need to integrate this triangular region. So the region D is a set of all points x comma y such that 0 is less or equal to x less or equal to 2, and 0 is less or equal to y less or equal to the line 3 minus 3 halves x. What we need to find is the area of the surface of the plane that lies in the first octant. So if we sketch that, essentially what we need to find is the area of this triangle that lies in the first octant. And here we have the point 2, 0, 0 in the x-axis, and then in the y-axis we have the point 0, 3, 0, and in the z-axis we have the point 0, 0, 6. So essentially we need to find the area of this triangle that lies in the first octant. So the area of the surface S will be given by the double integral over the region D of the square root of 1 plus fx to the square plus fy to the square times dA. From the equation that we are given fxy, which is equal to 6 minus 3x minus 2y, we can compute fx to be equal to negative 3 and fy to be equal to negative 2. So if we substitute those fx and fy, we'll have the double integral over the region D of the square root of 1 plus negative 3 to the square plus negative 2 to the square times dA. And we don't even need to use the region D because since it's only a triangle, what we have in the square root will give us a square root of 14, and then we'll need to evaluate the double integral over the region D of dA, which is exactly the area of the region D, which is a triangular region. So that will be equal to the square root of 14 times the area of the region D. And the area of the region D, so we have square root of 14 times the area of the region D. The area of the region D is equal to 1/2 base times height. So 1/2 base, which is equal to 2, times height, which is equal to 3. So that will be equal to 3 times the square root of 14. And this is in square units. Therefore, the area of the surface 3x plus 2y plus z equals to 6 that lies in the first octant, so this triangle, is equal to 3 times square root of 14 square units.